So hello again. Tonight we're going to talk about disappearing stars. You didn't notice they were disappearing? Well, there aren't that many of them disappearing, and you have to have really high power telescopes to see which ones are disappearing, but some are. So the history of stellar observations goes all the way back to humans carving things in stone that look like constellations, and then transcribing that onto leather, looking very similar, and then transcribing that onto ink and paper, and then eventually putting that on computers and databases, and you have planetarium software. As of us cataloging stars onto computers, we had sky surveys. Count them all, count every single one of them, because initially people would say, there's an old cartoon strip that Carl Sagan, as a teenager, was in a car with a date out in the middle of nowhere, and it was a convertible. He was looking up at the sky and talking to his then girlfriend, Becky. And his quote was, "There's hundreds of them, Becky." Because if you remember Carl Sagan, there's billions and billions of them.
Yeah.
Well, billions and billions, we flew past that many years ago. Now we're into the hundreds of billions. Last count I saw was in excess of 200 billion. That's just in the Milky Way alone, but that does include the large and small Magellanic clouds and the star clusters. The more we look, the better we look, the more stars we see. But we're also improving lenses and mirrors and improving the light sensitivity of instruments and making bigger and bigger cameras. And so we're apt to find more of them. But the stars we're looking at are in our galaxy. We can kind of look through the disk of light at the center of the galaxy and even see some brighter stars that are over on the other side of the outer arms of the galaxy. So it's not just like, it's 200 million. Assume there's just as many on the other side, 400 million. No, they're actually trying to see through in infrared and find as many as they can. But there are certain dense parts of the arms and the core where we can't see through to the other side because the number of stars is just so dense we can't pick them out separately. The stars we're aware of, the ones we've cataloged, are, let's just say, the easy to find ones. But as the technology improves, easy gets easier. But what about stars in other galaxies? Aren't there hundreds of billions of stars in the hundreds of billions of other galaxies? Yes, but unless those stars go nova, pretty hard for us to see individual stars in other galaxies. They're just a glow. The multiple hundreds of billions of stars we're talking about here are just in our galaxy alone, and we already know there are many billions of other galaxies. So as we look better with different instruments, ground-based as well as space-based instruments, we do surveys and we find many, many, many more stars. And the surveys have names like SDSS and 2MASS and Gaia. And there are multiple generations of the Sloan Digital Sky Survey. That's what SDSS stands for. I think we're up to iteration number 6 or 7. And every time they look with different instruments from different observatories, they find even more. Think of it as if the Sloan Digital Sky Survey only took place from a telescope with an imager of a certain generation, and that's the only place they look from, you can't see everything because the telescope can't look over the horizon. So the next time you do an iteration, pick a different telescope elsewhere on the planet, put the latest instruments in that, and now you can look out from there. All the ones that you counted before, assume those still exist. All the new ones you find, add those to the catalogs. Closing on 200 billion, estimates are we're not running out of stars to be found. We're just not covering the entire sky in a short period of time. So the surveys are kind of like panning up and down and looking across the sky at whatever they can see. And wherever they look, as they look with better eyes, they find more stars. There are astrophysicists that have estimated the stellar birth rate. In other words, not only are we finding more stars, but the Milky Way is producing from collapses of nebular gas and dust clouds more stars. There are about 10 to 20 new stars per year, with most of those stars being slightly smaller than one solar mass. So smaller than our sun, but that many per year. That's just our estimate. Could be more, but what about the ones that are disappearing? We know about stars that were in previous observing sessions. We know about the current observing session. And we know in the future, if we look again, well, we saw a star, there was a star, it's there again. That's not the ones I'm talking about. I'm not even talking about the ones that were there and during a certain observing session gone and then came back, because we'll get into all the different reasons as to why they could be transient loss of observing. I'm talking about the ones that were there, confirmed there, recorded there, cataloged, and then gone as of a certain observing session, never to be seen again. Those are the ones we're talking about. Here's the earliest one. Down at the bottom, you see black and white image of stars. This is a grayscale scanned film plate. So this was back when we did analog film on glass, and they scanned plates. And as they took multiple plates during a single overnight observing session, they discovered, hey, there's these 3 stars, and they're in this plate, and they're in this plate, and then all of a sudden, they're gone. They're just not there anymore. And they've never been seen since then. And that was their first example of vanishing stars. We'll talk about the reasons why they might be transient disappearances, but for 3 stars to be there, be confirmed as there on multiple observing occasions, and then all of a sudden, in the middle of a single session, there, not there, never there again. But there's no like explosion. There's no big blink out of it. It's just like they're gone, like somebody turned the light switch on. And you can see the other stars around the area where they were. They're just not there anymore. So let's talk about why stars would just not be there. Here's the laundry list, and then we'll go into the detail of each one of them. Optical train issue. This has nothing to do with freight trains. This is the path by which the light goes from the entry of the telescope to the image capture at the back end. Lens and mirror debris. Issues with the imaging chips. Image processing. Weather distortions. Temporary occultations. The one that really kind of like pushes out there, wavelength transmission transition to no longer detectable. So they go from whatever instrument you're using visible to invisible, because the instrument you're using cannot detect that wavelength. And then there's some other issues we'll rule out on a separate slide. So optical train issues. If you historically ever looked at Galileo's first telescope lenses or Newtonian's first mirrors, they would be unacceptable by today's standards. It would go, wait a minute, the lenses have bubbles in the glass, or that mirror actually has a wave because you had no technology for making the mirror perfectly flat or grinding it flat. And I know you put a silver coating on there, but it's all flaking off. Well, that's because they literally sprayed them on in the early days. And nowadays we use electrostatic discharge of metal to vapor in a vacuum, and we charge up the mirror, and then the metal particles cling to the mirror at like a 5 nanometer thick coating. And then we put other quartz coatings on top of that so they don't flake in oxidization anymore. Ripples in these coatings would be unacceptable nowadays. You'd send it back, give me one that's better. But if you did have these defects, you would know where they are because you see them in every observation. You would know how to work around them. And you would know that, hey, the next time we resurface that mirror or swap out those lenses, let's get rid of those defects. There would always be defects at the same X, Y coordinates within an image. across multiple images, different parts of the sky, you always know at those coordinates, you're going to have a little, huh. If you uncovered them in the initial analysis of your optical train when you first installed that telescope, it would be understood. If the telescope mount was altitude azimuth, then as the telescope moves across the sky and the imager rotates on the back of the telescope to counter field rotation, that little distortion would move in the image. Or it might be due to oxidation of your telescope mirrors or lenses. And we used to have this out at Fox Observatory for the two 13-inch Newtonian reflectors we had. The coatings were very damaged. But you know what? When you looked in the eyepiece, you never noticed that. But when you look down the tube, it's horrible. Replace these things. And they got rid of them and didn't replace them. What about debris? If you've ever seen a multi-million-dollar telescope being made, clean rooms, vacuum chambers, filtered air, all that stuff prevents any kind of stuff from being on the surface when the mirror is being created. However, once you put it out in a dome and then you open the shutter to the sky to do your observing, there's these little things called insects that can get in. Now, granted, if you have an observatory at 10,000+ feet, there's fewer of them. But if you have an observatory at only a few thousand feet, like some of the early observatories, insects can get in. Not a lot, just a few. And at the end of the night, when you're done and it gets real cold outside, you close the shutter and you trap the insects inside. And then you turn your mirror up. And when you turn your mirror up, the insects can't get out. They have no food source. They get desiccated. They die and they land on your mirror. And if they had any poop left in their body, then that's going to cause it to stick to the mirror. So until the next time you clean your mirror, you're going to have a little defect there where an insect gave its life to astronomy. But it also moves around because it's stuck on the mirror of the lens. It moves around as you look at different things, so you always know where it is. If it's floating debris, like dirt, dust, or pollen, then they can generally tilt the mirror down and then, tap the telescope, and a lot of that stuff will fall out the bottom. But you don't want to tap it too hard because that'll destroy your alignment. But usually they'll just work them out in post-processing. Imaging chips. They can have dead, stuck, cool, or warm pixels. They can have entire rows or columns. If you look at the Rubin imager in South America, yeah, it's definitely got some dead areas. But they know about them. They can take them out during post-processing. Here's another one. One-time detector issues. Alpha particles or cosmic rays. Yes, that happens. But the energy spike in the detector at that pixel or in those pixels is so high they're easily spotted. But as the imaging chips have more and more pixels and the pixel wells get smaller and smaller, and you have your observatory at a high altitude, the odds on getting alpha particles or cosmic rays is higher. And it's not a probability of 1, it's a probability of eventually. But they can deal with that in post-processing. They know what that looks like and they can filter that out. Back before the era of computers, when they had to stitch the imaging plates and film together, you need something between them to hold them together. And if you got the plates a little bit overlap, or you got the film negatives a little bit overlap, any stars that were along that edge could either be cut off or could be hidden underneath the seam. So you could have stars that were there, not there. And then in the next imaging session, they were back again. So we're not talking about those kind of things. Those are easy to deal with. But as we go to software for doing the stitching of multiple images into a larger field of view, that stuff's gone away because the software can dynamically pinch and can join up all the way to a pixel edge, and you no longer have the overlap issue. Weather, clouds, ice, rain. Well, you don't generally want to have the snow or the rain when you have your giant expensive telescope open, but upper atmospheric distortions. temperature variations can cause like waffling in the atmosphere. All of that can cause stars to blink out for a frame. So, you see a star, you see a star, you see a star, you take the next frame and it's not there anymore. And then you take the next frame 3 minutes later and it's back again because there was a little heat ripple that ran through the atmosphere. Astronomers know about this stuff, so they can deal with those kind of things. And in fact, the observatories actually monitor temperature and humidity and atmospheric pressure, and the software algorithms can remove refraction when you're observing low to the horizon. They can actually remove that bend in the image processing. What about things that are beyond the Earth's atmosphere that obstruct us looking at things, like satellites? As we get more and more larger satellites at geostationary, they're just there. So if your observatory is unlucky enough to be close enough to the equator to have the string of geostationary satellites, I'm sorry, you will not be able to see stars or galaxies that are directly behind the bigger geostationary satellites until later in the year when parallax puts you on the other side of the sun, and now you can kind of look around them. But now you can't see other things. So they know about these things and how to take them into account. They also know when a satellite, the evil Starlink satellite, goes overhead, they can actually know its track because those are published in pieces of information, and they can see that it's a fast mover. Like it's going across the sky, and you're not going to lose like several frames. You're going to lose like one frame only in that part of the sky. So they know how to deal with these things. The latest plausible explanation is, well, we've got stars that transition. Let's say they're a white dwarf, not at the end of their life because they're already a white dwarf, but over a very long period of time, let's say millions to billions of years, the white dwarf will get dimmer in visible light. It will transition from visible light to infrared. And as it does that, your visible only camera will no longer be able to see it. So it'll go to infrared. So you switch to infrared. Use JWST to see it. Well, if you take that transition, the next step is it'll go out of infrared to microwave radio, to UHF, to VHF, to ELF. And we currently don't have any astronomical equipment that will be able to detect stellar objects in the extremely long wavelength, or ELF. So if things are transitioning down to longer and longer wavelengths, then we need to create some new observing capability. But if they do make these transitions, at some point they'll fall below our radio observations and we just won't be able to see them again. But the ones that they're finding are things that are visible and then no longer visible. And I'm not talking about the things that show up and then are gone, like something that isn't there and then is there for a couple of observations and then gone again. This could be a black hole transiting across the sky, and it temporarily did a gravitational lens of a dim star that's much farther away that we couldn't normally see. It did a gravitational magnification of it, and therefore we got to see a star. Or in gravitational lensing, you might see the same star multiple times around the lensing. So that may be those three stars, but I don't know the particular stars, so I don't know if they were there before or not. But they're definitely not there anymore. Or it could be a stellar nova of a star in our galaxy, not a supernova, but a stellar nova. These happen, and when they happen, they go bright for a short period of time, days, weeks, maybe months, and then they go dim again. You can't see them again. So could be that. It could be a bright flaring of a dim red dwarf star that's too far away for us to see even in infrared. It could be, something in our solar system that is slowly rotating, and as it rotated at the angle so that we're seeing the sun reflecting off of it, temporarily we saw a star and then it was gone again. Not talking about that. Or it could be satellites that are very slowly rotating and they just happen to create a glint and then they're gone again. if any of these are the proposed answers or speculations as to why stars would disappear, remember the question is not that they were not there, then gone. We're talking about the ones that were there, known to be there, disappeared, and have yet to come back. So you may also hear of a thing called a Dyson sphere. This is also Kardashev civilization higher than us, where if you put out solar panels, you can collect a certain amount of the sun's energy for generation of electricity on Earth. But you can either cover the entire Earth with solar panels, or you can cover the entire sun at an orbit beyond Mercury with solar panels, and you can convert the majority of the sunlight into electricity. This is theorized. The construction effort to do that and the solar wind pushing out on that, I think would make this somewhat improbable. But even if you did create a sphere on the outside of your star that would make your star blink out invisible light, it would still be there in infrared because the sun would heat the sphere. Haven't seen that. And in 2022, there was a binary star system in the Large Magellanic Cloud within the Tarantula Nebula known as VFTS 243. That's the binary pair system. That was there, been there for a long time. All of a sudden, it just wasn't there anymore. And it's not like it came back again. It's just not there anymore. The Large Magellanic Cloud hosts about 20 billion stars. Not as many as our galaxy, but LMC is part of our galaxy. So in May of 2024, astrophysicists from the University of Copenhagen put out a paper that said, under the right conditions, a binary star system where one of them is collapsing into a white dwarf might not collapse into a white dwarf or even a neutron star. It might collapse directly into a black hole. But that would leave like a debris cloud. It would put an outgassing out. But if there were a companion star that was also at the right point, closing on becoming a white dwarf, it would act as an accelerant to the collapse. So if you think about it, if a star the size of our sun gets at end of life, it's going to collapse down to a white dwarf. If it's a little bigger, a little hotter, it collapses down to a neutron star. If it's even bigger and hotter, it'll collapse down to a black hole. Well, what if you had one that was going to collapse down to a neutron star and had a companion star that just added that extra little sauce of gravity when it collapsed down to pull that in, and now you've got a black hole? If there were no other stars around it, there would be no outgassing. It would all just go in. There would be no polar jets because the formula would be balanced by the addition of the second star. It would just all go in. And yep, if from a theoretical perspective, that's a possibility, but they have no data that says that's why VFTS 243 just disappeared. All of a sudden, you just had two stars that went off like a light switch and haven't been seen since. So there's a thing to think about. My thought is, if you have a disappearance like this that was there, and then suddenly is no longer there, if it is a collapse, you're going to get other things happening that may not show up in radio, infrared, or visible. I should say UV, not UC. It'll show up as gravity waves or neutrinos. So whenever you have a disappearance, go ask the folks at IceCube in the Antarctic, or ask the LIGO and Virgo folks, hey, did you guys have an event in the last few days in that part of the sky? If you did, now we've got some breadcrumbs to say it was a stellar collapse. But you have to look at the data. I don't think they've made that connection yet, but maybe once this video goes public, somebody will think about it. So in conclusion, stars in our Milky Way galaxy were there, and they're no longer detectable. Transient events are not the question. If it was there, then not there, then there again, yeah, we know about that. If it was stars that were not there, then briefly they're like something reflecting or something temporarily novaing, and then dimmed back down, never to be seen again, That's not what I'm talking about. I'm talking about the stuff that was there, no longer there, never seen again. And if it's due to a stellar collapse, shouldn't it have left something behind, even if it's only measured in infrared or radio? And if we don't see that, then there's got to be another approach. And if it's stars that suddenly don't become a black hole, but shift their wavelength below whatever observatory was looking at them, let's say you had an observatory that can only see invisible light. If that star did something that dramatically shifted it to infrared only, from that observatory's perspective, it just disappeared. Okay, ask an infrared observatory, ask a radio observatory, can you still see it? And if they can still see it, there's your answer. It transitioned from whatever your instruments are to instruments you don't have. Pick a different observatory with different instruments. But if it falls below the extremely low frequency, we don't have any observatories to look for that stuff. We have some submarine radio communications monitoring networks on the Earth that will do that. But once they fall below 1 hertz, 1 cycle per second, we have no technology for monitoring that. Certainly no astronomical observatories for it. If you look at one of these disappearances for days or hours prior to the disappearance, maybe it shows up as a gravitational wave or a neutrino. And some links. And then some videos on YouTube about stars that are disappearing. And there is actually a long-term survey. It's called A Survey About Nothing. This is a survey of telescopes that look for things that are no longer there. And then I add a link to the prior Broward astronomy video. Comments? Questions? Seen any stars disappear lately? Stars Are Disappearing is actually an Anton Petrov video. And then later on, I found a video that the title is, Why Have 700 Stars Mysteriously Disappeared? I guess so far I'm the only one that said, why don't we go back in history just a few days to a week and see if there's any gravitational wave or neutrino events in that part of the sky? If it really did collapse and disappear, either because it so dramatically shifted its wavelength or because it became a black hole, should be able to see something, at least gravitationally.
They don't make a pattern in the sky when they disappear, as far as...
No, that's the thing is, a normal collapse of a star, be it a white dwarf, a yellow sun to a white dwarf, like our sun would do, it would leave a planetary nebular cloud. It would leave something you could see visually. If it's a star that becomes a neutron star, you can see gamma rays, X-rays, ultraviolet, not so much in other wavelengths until the neutron star stabilizes, and then you can see it pulsing in radio. You can't see it visually anymore, but you can see it pulsing in radio. And if it's a black hole, then if there are other stars nearby, occasionally the black hole will feed, and you'll get an accretion disk around the black hole that is bright visually or in radio, and that's detectable. These have no leftovers. These are just, they were there, they're gone, there's nothing left, and they didn't come back. So that's why it's a mystery.
How many of these stars were captured in multiple observations, multiple photographs? Or are they they're on one picture and then they go away?
They have 700 of them that they've cataloged, have been long-term cataloged. They're very dim stars, but they're in our Milky Way. But they were there, they were recognized as there, and now they're not there anymore. And they've looked again, and they're still not there. I say, find the breadcrumbs of gravity waves or neutrinos, and now you've got to conclude that it was a stellar collapse. And I did include a link of the prior Broward Astronomy YouTube channel video called Vanishing Stars. We went from vanishing stars to disappearing stars. I think it's along the same lines as spectroscopically detecting biological signatures. It just is. And once you come to grips with the fact that it's possible, then it's a matter of found another one. But look for the signatures beforehand. Look at it in a very broad level of wavelengths, from gamma, X-ray, UV, visible, infrared, various radio bands, until you see there is absolutely nothing there anymore. And then say, well, how did that happen? Where did it go? Here's another thought that I think is probably less obvious. Billiard balls. We already know about rogue stars and rogue planets. These are stellar objects that basically got kicked out of their home. Let's say you had a binary star system and they were going around one another. And then all of a sudden, due to some flux change on one of the stars, the orbital synchronization changed and one of the stars became very long elliptically. At some point, when it's close to the other star, if anything happened, it has enough velocity that it could be kicked out of that solar system. So if you have a binary star system and all of a sudden something comes zooming across from another direction and gravitationally drags one of the stars away.
Yeah, but that would take some time, wouldn't it?
Actually, how often are we looking at the same stars? If you only come back like Gaia only looks at the same spot in the sky once a year. So if you only look once a year, and the really reason you're only looking once a year is stellar parallax, as the Earth is on one side of the sun, on the other side of the sun, you want different viewing angles. So you look, once every 180 days. But what happens in between time? If you get a star that's a rogue star and it comes zipping through there and there's just one star there, it could literally drag the other star out. And things don't have to move tangentially to our view. They can move from, let's say, closer to us to farther away from us, to further out into space. And if that's what drags the star away, and it was a dim star to begin with, we wouldn't see it anymore because it dragged it, beyond magnitude 21, and we just can't see any further, can't see any dimmer than that. So if a star came by and dragged it off or kicked it out, we wouldn't see it anymore. So there's other reasons.
Then we should see an apparently new star not all that far away from the old one.
Only if they were really
in
good.
apparent distance.
Only if they were really good with that cue ball and made the cue ball stop when it smacked the other star. If the rogue star had enough velocity and it didn't actually hit the other star, it just gravitationally accelerated it, then the star that came in would be very minorly affected. It would just like bend its trajectory a little bit. The star that accelerated away and left, it would leave nothing behind. So,
yeah, but it would still exist as a star.
How
and
far away?
Yes, if it did move further away to become invisible to us, okay, that's one possibility. But how many stars have vanished? How many did you say?
700, and they're counting more all the time, but it's currently 700 out of close to 200 billion. So
some of those would have moved sideways versus further away, and then there'd be this apparent new star. I don't know. It's an interesting possibility.
So in a survey like Gaia, let's say you were looking at a certain spot of the sky, and then you look to the next spot of the sky, and then zipping across, and you won't come back for another 180 days, is this rogue star that dragged away one of your stars deeper out into space where you can't see it anymore. You'll come back in 180 days, and you not only won't see the rogue star, you won't see the star that was there. So, poof, it just disappeared. So it got hauled away. But that's just, I don't have any evidence of it. It's just that's something that might happen. But did it happen? we would have to catch it in the act. So when they find rogue planets and rogue stars, do they follow them? No. They just, as they're taking their frames, they note that something's moving through the frame. And once it leaves the frame, it's of no interest to them anymore because they're not following that thing that's moving. They're following the background stars that aren't moving. So maybe what we need is a new effort to find rogue stars and then track them and see if they ever drag away other stars.
Are all of these disappeared stars very dim and
Yes.
far away?
Yes.
All of them are. That seems more than coincidental.
Yep. Well, the big bright stars, if all of a sudden Betelgeuse disappeared, we'd know it. Because somebody would go, why is Orion's shoulder missing?
Exactly, yeah.
So it's got to be really dim, really far away stars, but they're in our galaxy. And they're on this side of the center of the galaxy. Yeah. I just recently came up with the drag away. As you can tell, it's not part of the presentation. But until there's a program for tracking rogue stars to see where'd they come from, where are they going, we won't catch them in the act. So we went from, I'm not sure this evening's presentation will be all that interesting to, hey, comments, cool. Any other comments or questions before I stop recording? Hearing nothing.